So let's say you found the skeleton. How would you tell it's a dinosaur? You personally, how would you decide?
Well, interesting question. I don't know. I'd have to do some research on that.
All right, we are live, and there's Chesh
Oh,
looking
wait,
at
look,
all
it's
of you.
me.
Yep, that's you. Welcome, everybody, to the astronomy news with me, the Dapper Dinosaur. Obviously, Cheshire is going to be here for a little bit.
Hello.
A little bit, before she goes on a mission to go and get more viewers for us. She's on a secret mission after she leaves.
In uncharted space.
And, of course, we have Landon with us.
Good morning, good afternoon, or good evening, depending on your time zone and latitude, and perhaps even attitude. And hello from your friendly secular astronomer.
All right,
We're
and
sipping a great Costa Brown Santa Lucia Highlands Pinot
Up a little bit.
Noir, 2016.
there we
it is.
go.
Costa
Yeah.
Brown, Santa Lucia Highlands, 2016 Pinot Noir. Excellent, excellent wine.
All right, and last but not least, we have Ben Tobin, no relation.
Hi everyone, I have a cock and bull ginger beer.
All right,
Not as good.
Love ginger beer.
ginger beer is pretty good. Why aren't you drinking it out of a fancy mug there, Bent?
Think of it.
Oh, all right.
Going back.
All right, so today we are here to talk about some space news, and I think one of the interesting things is, so we not that long ago had our first known chunk of any matter of any appreciable size fly through our solar system from outside of it. But we've now had a second one come in that's been detected,
and,
right?
So, and then saying we're excluding, for example, cosmic rays or something like that.
Right, I mean a chunk of matter that is
that you can actually see.
Yeah. The sort of thing that if you hit it with your spaceship, it would be bad news.
Yes, or if it hit you.
Right. Well, I guess in space, it hitting you and you hitting it are about the same thing, right? Like, what's the difference? It's all
well, I guess
relative.
it's intent.
Yeah. Are you just burning towards it on an intercept? So, so this was, I assume this was an object where they tracked it over the course of a few nights, and they found that the eccentricity of the orbit was over 1, right?
Yes, and in fact, it's now has a physical designation 2I/Borisov, and Borisov is a amateur astronomer from the Ukraine who was discovered the comet, credited, and we call it 2I because I means interstellar visitor.
Okay.
So you'll find comets have P, like 1P/Halley. Halley's comet was the first known periodic visitor that wasn't already a planet.
Right.
And so the eyes are now the interstellar thing. And this is nice because unlike an asteroid that just sits there and sort of
just bees an asteroid,
like a rock, right?
Yeah.
Comets outgas. They emit stuff. They have a coma and other sorts of things.
Right.
And so we get to know a lot more about its composition by looking at the tail and the coma, which is quite exciting. But as you said, it has a eccentricity. But the eccentricity is measured at 3.356.
Well, that's pretty high.
So it's pretty. It's pretty eccentric.
So is that because it's traveling terribly fast, or because it's not going to end up very close, so it's not being very strongly affected by the sun? What's going on there? Why is it such a high?
Both. I mean, the object's nearest point to the sun, I believe, is around 2 astronomical units. That is, it approaches.
It's not close to the orbit of Mars.
Yes, it's about orbit of Mars. In fact, the distance, I believe, is they come within 2 AU. So 1 AU is Earth's sun distance.
Yeah,
so
the average mean.
Twice the Earth, twice the AU there. It'll be its minimum spot. And
what was the previous one's closest approach? It was significantly closer, wasn't it?
Yes. So I think that the one eye, and it's the one that says, Omu, something like it's something. It was
Oumuamua.
Oumuamua.
Yeah, something like it was Hawaiian. Those crazy Hawaiians.
Yeah. And that was the first one that actually got much closer. But unlike that one where we saw it kind of on its way out, this one we were watching on its way in. It was discovered in August at the end of August, and it will pass closer to the sun, I believe, around December 9th, I believe, or 8th, 9th, if I recall correctly. And it has its closest approach to Earth, which is not very close, but will be towards the end of December. So it's moving at a pretty good speed. It's around 32.2 kilometers a second. Oumuamua was only at 26 kilometers a second, so it wasn't as. But what we mean is that the velocity is such that it's not orbiting the sun. It's not gravitationally bound to the sun. So it's certainly its orbit is being deflected because of the sun's gravitational field and it's bent, but it's zipping on through. The exciting thing, of course, is that that we can see the composition. This is a comet that came from outside of our solar system, so it's an interstellar comet. It most likely was a visitor, a comet from some other star system, and it just happened to be passing through, and we happened to notice it.
Okay, so do you think it would have been kicked out by some kind of gravitational interaction with maybe a planet or something, or I guess an exoplanet?
And we certainly have comets that do one pass around the sun and get ejected.
Yeah.
So that's not there. It's just the unusual thing is that one of their comets has come in through our solar system, and we get to look at it.
So you're saying it's not aliens then?
Well, I mean, it is in terms of it being a it's got a nice coma surrounded by
But it's not aliens in the sense that you would write a sci-fi story about it.
No, but in fact, in some ways, when we look at the composition of the gases coming off of it, it is very similar to comets of our solar system. So we know at least so what we know. We know that there's at least a comet from some other star other than bound to our own, and that comet is similar in composition to comets around our star, the sun.
So maybe that's confirmation that our star system isn't super unusual in terms of at least its comets. We have pretty typical comets, it seems like.
Yes, and I say, and the size-wise, this is a and it's debated because it's hard, particularly when it's far, to see what's the nucleus and what's basically being obscured by the gas boiling off of it.
Right.
But it's somewhere in the order of around 1.4 to about 6.6 kilometers in diameter. So that's about a mile to about 4-ish miles if you're metrically.
Not gigantic, but that's a pretty solid chunk of ice there.
There's other that's going to be larger or smaller, and again, it kind of depends upon is this a rock with a ice dusting around it, or is this a fairly compact icy body with very little dust? I mean, we're learning more about it as it's going on, but you study to try to figure out.
But I guess we don't have a good mass estimate, do we?
So we do have in terms of its again its dimensions, but you talk about the actual size of itself is not. Yeah. The size is more of an estimate as to where it might be going. In terms of it reaches its closest point to the sun on December 8th or 9th, depending on your time zone, and it's Earth full spectrum. Now, this is not going to be a comet that you're going to go up and look out in the sky. You need a modest-sized telescope to see this sort of this comet. It's certainly going to be something that you would need to probably go to your local astronomy club with someone who has a decent sized telescope or an observatory to see it if you wish to see it.
Or up to the Mount Lemmon Observatory, right, Bent?
Exactly.
Yeah, I think I told you, Landon, but Bent and I, we went up to the Mount Lemmon Observatory near Tucson, Arizona, not that long ago. That was a lot of fun, and I believe there's currently an invitation for when Chesh ever gets her way out to the southern U.S. I believe there's an invitation for her to come up and go stargazing at the same observatory.
Lemon Sky Center.
So that's still a little bit in the idea stage. But if that happens, I'm sure that it will become the topic of some kind of live stream or something, right, Chesh?
I'm working on it. We'll get there.
All right,
One,
yeah.
one stop at a time. We'll be traveling all over the place in the next year. I've got so many places and so many people I gotta go meet.
But only one of them has the largest reflecting telescope available for public use in the entire. I think North America might be the world.
That's true.
So, oh wait, you have to put your hands up when you do that.
That's true.
Otherwise, you won't know if it's true because the angels won't tell you.
Yeah, that's right.
So anyway, so we're pleased to see that at least that our comments and a comment at least one other solar system have a lot in common. We're going to be continuing as the comet gets closer to the sun. It's going to be brighter, but again, too faint to see with the eye. But we'll get more spectroscopic data and learn more about this visitor from another world. In fact, another solar system, another star system.
Nice.
An interstellar visitor.
All right. Well, that's pretty cool. So, do you think that we just got extraordinarily lucky and detected 2 of these rare events, or do you think they're more common than we thought in the past, and we're only now getting the numbers of observers and technology the level where we can actually regularly detect these as they happen?
My speculation is that this has happened certainly before, but we have a much better coverage of the sky, and a lot more, not only a lot more things looking, but also particularly with the digital age, we have detectors can detect very faint objects, and we have this computerized system to compare it against the background to say that's different. What that is, right? And that's essentially part of how also amateur astronomers scanning around discovered this object as well. So
I imagine like once we've detected it once, we now kind of have a little bit of a better idea of what we're looking for when we're looking for something like this that would help either an algorithm or somebody who's seen it now be able to find it.
Yes, and so we had one in 2017 and one in 2019. 2 points does not make a rate, or a very accurate rate.
Right.
And so the question is, are we lucky? Are we getting better at finding it? And that's one of the things where we're going to enter into an era of what's called survey telescopes. So things like LSST in the visible range, and square kilometer array in the radio range, as just some examples of scopes that are scanning the sky continuously are going to be able to pick up stuff which currently we're no doubt missing. Okay. So we don't know how many we've missed.
Right.
And it'll remain to see whether or not our ability to detect more stuff will come up with more visitors, or perhaps we just happen to have the 2 in our lifetime and that's it. Stay tuned.
Okay. Now, out of curiosity, what are the orbital inclinations on these 2 objects that we've encountered?
The inclination of Borisov is 44 degrees. So essentially, if you think about the solar plane, right, and there it's basically coming at a sort of half right angle in terms of passing. But again, it's not an ellipse. It's not a
right.
orbit.
Its eccentricity is over 1, so it's going to be a hyperbola, right?
Yeah, hyperbolic orbit.
Yeah. Okay. And do you know what the inclination for Oumuamua is? Because I would expect them to just be kind of at any given angle as we detect these. Because why should they be clustered around any particular angle, right?
Yeah, it's I recall the inclination of that was 122 degrees. So that would be
kind of the other way.
If 0 is the plane, 40 degrees is up. It's going to be past 90. 30-degree inclination.
So it's coming in sort of retrograde relative to the rest of the solar system, but very inclined.
Yeah, but it probably thinks we're retrograde. So.
Well, I mean, yeah, sure. So yeah, because what I would
It's
think,
all relative, Dino. It's all relative.
I know, but I happen to live in the solar system, so for me, prograde is prograde for the solar system. It's just how it is.
But as
I
a
live
dinosaur,
here.
aren't you particularly triggered by large objects?
We need a trigger warning for Dapper because of asteroids and meteors.
So you know what? Look, I lost a lot of friends at the end Cretaceous, but I'd lost a lot of friends before that. Whatever. In fact, actually, yeah,
Are you with that book? All of my friends are dead, based on you.
But
yes.
But as I say, we're trying to get a better idea about potentially hazardous objects, and with a hope of maybe that the object hit the Yucatan Peninsula about 65.5 million years ago as being one of the last major big chunks to upset the biosphere. Let's see if we're smart enough.
That'd be
to
nice.
get to the point where we can, at the beginning, just detect to see where it's coming, and detect it long enough in advance so we can do something about it should we choose to do so.
And we got to find a way to keep Bruce Willis alive because he's the one who's going to save us once we find it.
Something of that order, yes.
Right. So people who are looking into things like cryogenics and life extension, start working on Bruce Willis, please. Because otherwise, who's going to blow up the asteroid or whatever it is? Although I guess blowing it up is actually not a very good idea because then it's just multiple chunks that hit the Earth, which isn't really all that much better.
Yeah, I mean that's one of the common misconceptions is if you got an object heading towards you, breaking it into smaller pieces doesn't help very very much unless you break it up into such a large. Do it early enough that you have such a large fan out. The problem, of course, is that when it's coming right for you, as they say in South Park, it isn't obvious that it's got you dead in your sights. You'd be more likely to say, there's a certain percentage chance that it could hit the Earth.
Right.
So if you shatter it into lots of pieces, you'll improve the chance that some pieces will hit the Earth. And part of the issue is kinetic energy and part in the atmosphere and so forth. So keeping it in one chunk and hoping it misses you is one strategy. But of course, if it doesn't, then you're lost on it. So there are much more sophisticated ways to try to nudge something out.
I always think that the early detection means the earlier you detect this potential collision, the less energy it's going to take to deflect that object from a path that's intersecting Earth. So
very, very good because it takes energy to take a massive blob and shift it, right?
Right.
And you have to and you have to have an enormous amount of power to do it fast.
Right.
So what you want to do is detect it as far in advance as possible, so that things that have lower power and also more practical can nudge it in a way to move it out of.
I have to admit, the entirety of my understanding of orbital mechanics comes from playing Kerbal Space Program. So, which actually, you know what? It's a two-body patched conic system, but even two-body patched conics, I mean, it got us to the moon, so it's not that bad of a system for simulating orbital mechanics, right?
Yeah.
It doesn't do Lagrange points, except I think you can still do... No, I don't think you can. You can't do any of the Lagrange points, but whatever. I guess you can do the Trojan Lagrange point, like, what is it, L2 and 3 or something are the ones both ahead and ahead?
The Trojans are the asteroids associated with Jupiter, and they're Jupiter's L4 and L5.
4 and 5,
they're essentially 6 degrees in front of and 6 degrees behind on the orbit of an object that's roughly circular.
Right. Yeah, you can technically do those in Kerbal Space Program, but that's only because you're just matching essentially the orbit of whatever the planet is that you're trying to get to the L4 or 5 of at that point. There's not actually the 3-body interaction. Although I saw a mod for 3-body interaction, and it actually just ejected a bunch of the moons from the system that the game has, because it turns out the game developers didn't really take that into account.
Yeah, and so just intercepting an object like this is hard enough. I mean, we
I mean, you have to get to
estimated that they're going to get a CubeSat up to this. It probably take about 5 years of development to try to get something into the spot where at twice the Earth Sun distance, it would be able to encounter it, let alone do something significant to nudge out of the way.
So we should start building that now for next time in 5 years.
Yeah. So the thing you want to do is try to detect these things as far in advance as possible. Now, there's kind of an upper limit on how far in advance. So if we see an object that's several hundred years away from hitting the Earth, the problem is that the orbital uncertainties are so large that that's not really useful. It's usually around it's around somewhere around 100 years is kind of the upper limit to being able to do any kind of forecasting of percentage chances this thing will hit the Earth.
That's a pretty good amount of time to get something to go nudge it, though. I mean, if there were a comet that's going to hit in 100 years, I feel like we could probably get together a rocket that has a couple other rockets strapped to it that we could plant on that thing and
do
nudge something.
I don't want to close my eyes. I don't want to fall asleep.
So, and of course, doing something like dusting, the easiest thing to do is to dust one side of the object with really reflective dust, like aluminum powder, to make one side shiny.
Right. So then
the other side is dark.
Radiation pressure just pushes it as it.
Oh, that's cool. I like that idea.
And so basically, it would be kind of like you just have a big, like it'd be like a one of those pellet, the game you'll play for the shooting paintballs, like a paintball.
Oh,
right?
okay.
A giant paintball stuff where you just go poof and you put this on the side of the thing, this nice shiny aluminum bit, and then that over a couple of decades is enough to nudge it. The nice thing about it, if you nudge an object even in a random fashion, the chances of it, if it's going to hit you and you nudge it, you have a good chance of it not hitting you.
Right, no matter which way you nudge it, really.
If it's going to miss you, there's only a very, very specific nudge that'll get to the point of hitting you. So nudging something that might be hitting you and might be passing you by isn't that bad. It's only when it's got you in the sights that you want to nudge it. Now, and again, blowing stuff up and shattering it to pieces is
way more work than we need to do,
and more dangerous.
And you gotta because the forward momentum, when you blow something up, all it does is it spreads it out, but it still has the same forward momentum, the same mass, right? And that's going to hit you with.
So now we're just going to hit with a bunch of shrapnel, which could be X amount large.
Right.
And so you sit there and say, okay, they're shooting at me with an AK-47 bullet, or they're shooting at me with a shotgun blast.
Right. Like, is it really that much better to take the shotgun blast? Maybe, but still, let's not do that.
That would depend on how far away they are.
It's like
how accurate they are.
Doesn't matter. Yeah, exactly.
Right.
This is back to the thing. So there's a number of various methods you can use to try to push things through. And some of it is just having a rocket with some mass that the gravitational attraction will pull it, and you basically gravitationally tug it on there. Now you say, well, giant object, several kilometers in diameter, small rocket, but if you do it a long enough time, that mass deflection will move forward. Again, you just need a couple of centimeters per second speed change, and you'll get it to miss.
Send up an ion engine. That'll get it some thrust for a long time.
I mean,
all right, I gotta swap out. I'm gonna go tell everybody the planet's over here.
Go get us some viewers.
Always a pleasure, by the way, and cheers to you, man.
I don't have a.
Get a mug.
Get a mug.
It's got stupid grapes instead of a dinosaur on it, Chesh. Come on.
Sorry. I don't even have my own face mug. Come on.
I don't either, actually.
All right, I'll see you guys later.
All right, bye.
Yeah, later. Thanks. But as I say, you want to have enough of a thing in advance. Other objects you can have you basically land a rocket on the object, and you basically fire the rocket off and basically do thrusters. Or you bore a hole and basically have an explosion that comes out of the hole to create kind of like a cannon.
Right.
That's what rockets are to control explosions.
I have a quick question about the idea of coating it with some kind of highly reflective material, and that is so. the end effect of that on the object's orbit would simply be to raise its aphelion and perihelion, right? Wouldn't that just raise the orbit overall? Because the radiation pressure is always pushing it away from the sun.
Well, but there's also the Yarkovsky effect. For the size that the part that's not shining, these objects are very, very dark. It's going to absorb photons from the sun.
Okay.
And provided the object has some spin, which they all they do.
Seems like they would all.
When that thing, the part that's facing the sun is going to absorb and get hotter. As the thing rotates, that thing that got warm will rotate away and start to cool off.
Oh, so that radiative pressure will also push it.
Yes. So you get a net effect of photons coming if you're the object coming at you, right? As from the sun.
Right, and that'll push you away.
And you rotate, and then there's another vector as you emit photons that cool off.
Okay.
On the outside. So the net vector is off to the side.
Okay.
So in other words, if the photons come in this way, and then they leave that way,
right?
The net effect is to push it that way.
It's sort of going to push you in like a normal or anti-normal direction, huh?
Yes, and depending on the speed of the speed of rotation, right? Because if it's not rotating at all, then you just have one spot that would absorb the heat and radiate it back, and that's not going to do it directly. If an object is rotating very fast, you'll get this sort of uniform spinning that will cause it to fling out photons in all directions and not get much effect.
Right.
You want something that's somewhat slowly rotating. Putting boring a hole and loading fuel to have it act like a cannon is not going to work with the object as a gravel pile. Right.
Right. It'll just push through it.
Yeah. So as I say, the thing you want to do is to have years or hopefully decades of time,
right? And
then figure out the best way to figure out if it's actually on the hit parade, as they say, and then what to do about it. So there is a website that has lots of detail about what they call potentially hazardous asteroids, right? And if you it's CNEOS, CNEOS.jpl.nasa.gov. Or another way you could look for it, if you look up Century Earth Impact Monitoring, you will see a list of potentially hazardous objects, the current ones they found, the probability that it's going to hit Earth. Probably the one that has the most significant probability right now. There's an object called 2010 RF12, and that has a somewhere between 2095 and 2117, and it has a 1 in 19 chance of hitting the Earth.
That's something we should probably keep an eye on.
Right now. Now that is with a 70. Let's see how many. Look at this details here.
Thank you, Bob Knob.
This is not a large object. This is like 7 meters in diameter, so it's about
that's
like 7-8 yards. But that's
I'll probably be fine.
Sort of the size that Chelyabinsk, the recent object that broke up over a Russian city, did a lot of damage. So it's okay. It's not a big thing if it hits us, but it'll be
not an existential threat for humanity, but it's still not going to be fun for whoever it hits.
Yes. Now, if you talk about the thing that's probably there's an object that called 1950 DA that is in the year 2880.
I'm sorry, that was 2880?
2,880, right?
That's way more than a century.
Too far away for noise. It has about a 1 in 8,300 chance of hitting the Earth.
Okay.
But it's an object which is about 1.3 kilometers in diameter, about a mile in diameter.
Ooh.
Right? So
that could cause some damage.
So it's something that's caused damage. But of course, people say, but at this stage, so far out, all those more chaotic processes going on in the solar system and radiation spins and so forth makes it basically useless to try to predict an orbit that far in advance at that accurate
right, because it's going to interact gravitationally with something else during the next 800 years, most likely. And what's that going to do to the orbit? I don't know.
And it has, stuff, if it's got any volatiles, are going to be escaping and pushing and nudging. So,
yeah.
So that's really kind of a bit too far out. If I look at something that's somewhat serious, there's a 1999 RQ-36. It's an object that's about half a kilometer in diameter.
Okay.
So that would ruin the day of a continent, let's say.
Yeah.
As opposed to the there, and its odds are about 1 in 2,700, and its impact ranges are between the year 2175 and 2199.
All right, that's something to definitely keep an eye on.
So to say, if you go and look at this this website, you'll see a table, a list of these current objects there. You will see ones that are currently tracked. I mean, one of the problems is that we see something that looks potentially hazardous. It zips by and say, "Oh, we didn't notice that was coming." It zips by.
Right.
We try to get enough radio pings to get enough of an orbit to hope we know where it's going and whether it's going to come back again. That's
right. These are just the ones we know about.
Yes.
We don't know about the ones we don't know about, as Kent Hovind likes to say, and this time he's right.
And so there's a whole database you can download and do things.
Okay.
But when we first see something, we give it a little risk because we don't know where it's going, right? It's a combination of being certain of its orbit and it's something of significance that's going to give us more of a. But Sentry, Earth Impact Monitoring, it's Jet Propulsion Laboratories, Center for Near Earth Object Studies, and there's a whole set of telescopes, like for example, there's a group of telescopes on Maui and Haleakala that are looking for objects. There's other ones in the Atacama Desert, and so we have these going to be these great survey telescopes. So hopefully, the chances of us being caught unawares are low. Now, there still is the case that we could get an interstellar visitor that's got a name, number on it. Like, so if we're scanning the skies around our solar system and finding lots of objects, it's the one that comes from out of the blue.
Right. How are you going to predict that?
That you just hope you have enough of a time, because how much time do you need? You probably, I would guess that if you're somewhere, if you only have like a year to 2 years time, your options are pretty limited in being able to do something about it. So had this object, interstellar visitor, been something that's going to hit Earth, we'd be in a desperate situation right now.
Okay. Now, one idea I think I've heard is, well, let's say we find out, okay, there's an object coming in from interstellar space. It's likely to collide with Earth in, say, 2 years. Could we load a nuclear device onto a rocket and detonate it far enough away to give it a push, but not so close as to, pulverize it? Would that be a thing?
But one of the things that, and nuclear devices in outer space,
I know it's not a great thing, but
are not that. They're not that effective in terms of, because a lot of the.
But with only 2 years,
inertial oomph of a nuclear explosion on Earth is popping a hole in the atmosphere,
right?
Popping a bubble and having that shockwave go through. When you've got a nuclear device out in outer space, most of the mass is just the device itself. Right. It's not that much mass compared with if we're talking about an object that's big enough that you want to try to do something desperate. Having a tiny rocket with a tiny nuclear device that goes buzz isn't that much of a change. Moreover,
what if we just put
what you don't want to do is sit there and say, okay, well, we had an object that's going to hit us. Now we have an object that's slightly radioactive that's going to hit us, right?
Right. Well, actually, at that point, I feel like it's sort of like, oh, you got shot by a cannonball, or oh, you got shot by 8 cannonballs. It's like, well, okay, but I think the one cannonball was going to be sufficient anyway. The other seven are
Red-Eye would
superfluous.
say it's a choice between being eaten by a zombie or eaten by a radioactive zombie. They're still eaten.
Yeah, like what's the difference? Like at a certain point, I'm just like, I don't care if it's radioactive anyway.
But now let's say the object is on the order of that one, like a half-kilometer diameter.
Okay.
Do you do yourself a favor by letting a radioactive version of that hit a spot, or do you try to go and plant something on the surface and fracture it, so now you have smaller objects hit a wider area, right?
Right.
So you might say, what do you mean by that? Well, you might have something, if it hit Central Asia, that would cause mass destruction within a region of Central Asia, or you split it up into a bunch of smaller pieces to have catastrophic events over a wider Eurasia, Africa, so on, right? And then you add it to radioactivities. So it's not necessarily that what you think is the macho, let's go and bang on it.
Right.
You're more wanting to nudge it out of the way. But the big thing over again is you need time. The more time you have, the less power you need to get the same effect. The more time you have, the more ability to develop options and backup options, right? Because that's the other thing, is you don't want to have just one option and say, okay, we've got this, we're going to land this rocket on the thing, bore a hole in it, and launch the rocket inside the hole, acting like a cannon to push it. Right. And what happens is you're sitting there, and you've got some computer malfunction, and the computers do the Microsoft equivalent of blue screen of death, and you sit there and say, oh, well, okay, let's try it again. No, so you want to have, if it's really serious, you want to have a series of things you're doing to it. That means you have to have time. So you want to be looking really well.
Bob Knob, who's not a fan of Microsoft, says that's why we don't use Microsoft products in space.
Exactly.
Yeah, that's probably a good point. So, okay, let's say a third interstellar object is detected, and its closest approach to Earth has a 1 in 3 chance of actually intersecting with Earth. It's 2 years from now that's going to happen. Landon, the president, we'll just assume it's still Trump because, he's going to probably be president for the next year or so. Trump says, Landon, you're our biggest scientist. Billions and billions of dollars are at your disposal. How do we stop it? And that's on you now.
So I would do a combination of things. I would start with some programs that make a guess as to the composition of the object, and do heavy launch stuff. So I would take some of the heavy launch stuff that they're planning on using and commercial things, and begin to tailor those things to be able to get outside of Earth's orbit, or Earth's gravitational well. Because it's one thing to send something up to the space station, another thing to send it out of the gravity well, and then
right. That's going to take a lot more delta V.
Yeah. Another thing so I would start with that. I would have a combination of observation programs to try to get as much intelligence about the object, its nature, so that we have a series of interceptors, right? So one of the things in particular, if it's there, is to take a fairly lightweight probe on a like a Delta Heavy V rocket, and give it a really good inertial thrust. Like, for example, they kicked out the New Horizons probe towards Pluto, and get that thing as fast as possible to approach it, and with a telescope on it, to give you relay back in sort of real time more information about this object. Does it have a coma? Is it just a solid object? Is it a gravel pile? Because that's going to tell you what kind of things you need to do in order to start to deflection set. I would certainly try to get a lander program going to be able to land on the object and do a push. But for example, landing on small objects, even objects that are on kilometers in diameter, is a very tricky problem. I mean, we tried that. We've had marginal success with bouncing off of objects,
Right.
that we orbit, because there's not much gravity there, right?
Could we use the Legend of Zelda solution where we just have a hook shot and then we just stab it with a harpoon and then use spears?
That's
Is that an option?
I'm trying to remember the name of that. It was that European object that has that very long name.
What is it, in Basque or something? It's got a crazy long name. Sorry, I just like to pick on Basque.
I about to say its name, but it's something like CheshireViq, I think, is the end of that long.
Oh, okay.
Frame. This is an object, and it had Philae was the lander, and Philae had exactly that. Philae had these hooks they were going to grab. It's going to come down slowly, and then got it near, fire these harpoon hooks to sort of stab into the to hold on, but it bounced off of the surface, and it didn't have enough
firepower, maybe.
Well, probably the surface was like hard rock or shale. It kind of ricocheted off and didn't penetrate in, as it wasn't a as dusty of a thing, or it had a dust over a really thick, dense rock material.
Okay.
And then the comet itself didn't have enough mass, and so the thing kind of bounced off and bounced around on the surface until it came to rest, unfortunately, inside a crack where it couldn't get to solar cells. It was
so video games have misled me about the reliability of harpoons.
Yeah, because imagine if the object is actually highly metallic, right? Or imagine it's worse, it's got a dust coating on top of a really solid center. You have harder, so you don't have you have sort of a thin, soft skin and a really hard, metallic undercurrent. So that's part of the thing. Is what you start doing is you immediately your high priority is to launch a probe and a series of probes past it to do observational work, and then you start someone who's doing an interceptor to try to do a lander. And as you gain more information about the thing, you have subsequent landers adapting to the more conditions. So you'd want to have something that tries to harpoon it first, and if it's a really nice fluffy thing, you say, okay, we now know that it's a puffball, and so we can then begin to develop things to scatter a puffball, as opposed to it's a hard object, and we need to have a more gentle approach to it. So you want to get there fast, but you would have to put in a lot of fuel on board to turn around and have retro rockets to slow down, so you gently,
right, because you don't have time to just intercept it and its orbit. You're going to have to do some like brachistochrone intercept trajectories on this thing, huh?
So so you want to have a series of these probes that is going there, and the probes that arrive later are going to gain from observational intelligence and probe intelligence of the first ones. So you don't have one shot.
All right. And by the way, I know I haven't been super interacting with chat, but I do appreciate everyone. The Flightless Bird is here. No Name, Bob Knob. I think I saw Amos Marcos earlier. Mai is here. Who else have I been not neglecting? We got Beach Prize, Angie Dell 66, Tucky McNubbin, Angie Dell 66. Yeah, I think I did. Oshkosh for Josh. And if I'm missing you, sorry about that. So, all right. I'm still not too optimistic, even with you in charge of our defense program, for a interstellar object with 2 years to hit Earth.
2 years is not. I would prefer about 10.
Well, you don't have 10. You have 2. You don't get to choose.
I mean, we might even have 2. I mean, this object, it gave us a couple of months.
Right.
That's kind of is the.
This love is here.
We've had objects that have been, embarrassing size that has passed between the Earth and the Moon. We only saw it as it was on its way out, right?
Right.
So, but if you look at if you say the really, really big objects, I mean, things that are 10, 20 kilometers in diameter that could potentially hit the Earth in the next 100 years, we think we know somewhere in the 95% of those objects. When you get down to the ones that are in the half kilometer, we're down in maybe the 40-50% range.
Right.
And if you get down to 100-meter diameter, which is still, something
gonna
that
be a
would
bad day for
destroy
somebody.
a metropolitan region,
Right.
and then some, right? It would be really bad things. You're down in like 20% of objects, we think, right? Given the rate that we're finding it in.
Right.
So, when is it really too small to bother? Well, it depends upon if it has your number on it or not. I mean, that 7-meter diameter thing is for object of curiosity.
Right.
I think when you get into the 20, 30, 40 meter diameter stuff, that's when it becomes serious enough to create a significant meter crater and regional devastation.
Okay. So I think there's been some other astronomy news. I think we can probably mention the transit of Mercury real quick. I guess from a scientific standpoint, it's more of a isn't that neat than something we discovered a lot from, right?
Yeah, I mean, of course, it was one of the things that when we started getting ideas about celestial mechanics, that objects actually passed in ellipses. They were not on the same plane. We had enough of a certainty we could begin to predict stuff that people like Kepler were able to predict 2 planets that pass in front of the sun. We have 2 planets that are closer to the sun than Earth, Venus and Mercury. So Venus and Mercury are 2 planets that can that are inside Earth's orbit.
Right. So they can transit.
That appear to transit or pass in front of the sun.
Right.
And we had a nice one of Mercury the other day that passed through. The next time Mercury passes, it has a periodic cycle. The next one actually, because of the way the orbits work, it skips one of its pass points. So it'll be like 2032 before it shows up.
Now, Ben, did you get a look at that? I know you have some solar filters.
Yeah, and it was a nice thing to see that the transit of Mercury was something where Mercury's actually, if you have reasonable visual acuity and you have safe solar filters, you can look up there and basically it sort of looks like a sunspot,
but it moves too quickly.
But
right?
but the sunspot because sunspots are sort of have fuzzy edges. This has a sort of crisp edge.
Okay.
But if you have a reasonably good visual acuity, you can see it. The transit of Venus, on the other hand, is Venus is actually, because it's a bigger planet and it's closer to the Earth. The transit of Venus is actually a much easier thing to see. So,
when's the next one of those?
But let's say, for the Mercury transit are on average about every 6 to 7 years, but then you have a gap. Okay. You can have another gap. In our particular case, you can have the gap can give you a long period. Now the transit of Venus, however, those are fairly rare. And we had one in 2004 and another in 2012. Prior to the 2004, so the way that works with cycles is that you get 2 transits of Venus 8 years apart.
Okay.
So the 2004 2012 was one of those pairs. The previous pair was in 1874 and 1882, I believe, was the.
Oh, so we're not expecting another one for a while, huh?
So yeah, so the because it's not going to be, it's going to be a while before the next one shows up here. But I say if you look at the dates, the next one is going to show up on it's going to happen around December 10th or 11th, depending on your time zone, year 2117.
All right, Bence, get your solar filter ready. Maybe get a bigger one in preparation for that, because I'm expecting you to film that for me.
Okay.
It's visible in Eastern China, Korea, Japan, Taiwan, Indonesia, Australia.
I would recommend Japan, mostly because of those places. That's my favorite one to visit. So Bent, are you getting ready for this?
Yes, I'm almost ready.
Okay, so you've got your solar filter.
Got 2 of them.
All right, but are those going to fit over the telescope?
Yeah, I don't.
Or you're going to put them over the eyepiece, I guess, instead of over the collector?
You put 1 on each side.
Well, wouldn't that just make the sun impossible to see at that point? I don't know how this works.
You always want to put your filter on the front of the telescope.
Yeah, not the
back.
eyepiece.
Yeah, just say. But anyway, so the year 2117 and then 2125 are the next pair that'll show up.
Okay. Well, we've got Bent on that, so he's going to be there for that. So stay tuned. Everyone, start holding your breath now, and I'm sure we'll be just fine by the time we get there.
The eastern U.S. and some of the partly visible in the western U.S. is for the 2125 transit. So actually, Venus was actually is big enough. It's about it appeared to be 1/30th the diameter of the sun. That with the typical sort of clip glasses, you see, look there and you see the definite dot moving.
Okay.
And it takes several hours for it to go across. It's nice little.
Is that the kind of thing that would actually noticeably dim the ambient light in an area?
No. So the sun's angular diameter is roughly 30 arc minutes.
Yeah.
The Venus, when it's near, on the same side as the sun as the Earth, is about 1 arc minute. So it's roughly 1/900th so it's only blocking like 0.1% of the sun's light, and so you'd have to have a highly accurate photometer to notice it's slightly there. But when we detect planets or other stars by the transit method, we're doing the exact same thing. The starlight, while the planet's in front of it, drops a little bit and.
Yeah, but we also have much more sensitive equipment than the average person's eye.
Yes.
No, not necessarily much more sensitive than my eye, because dinosaurs are better at vision than humans are. So,
but
take that.
That's why you want to go to a total solar eclipse, because if the moon's in the right part of its orbit and you're in the right spot underneath the shadow, 100% of the sun can be blocked.
Right. All right. Well, that's pretty cool. It's one of those things, like it's a neat little coincidence in the solar system. I don't know that there's a whole lot of new stuff to be learned by a Mercury transit. I don't think there is really. Did we learn anything new through that?
Well, the Venus transit gave us some information. Again, we did another confirmation of the distance of the Earth to the Sun by a pair of observers. I was in Arcetri, Italy, above Florence, and my colleague was in Madagascar for 2004.
So you found out that the sun is 30 miles above the flat Earth, right?
Yeah.
No.
Yeah, and so our we now have a pretty good idea about how far the sun was, but our distance was 149,596,765 kilometers. Plus or minus 3,543 kilometers. So we had a 0.0237% uncertainty.
So
we nailed it down pretty much.
That's pretty good.
A lot better than Captain Cook and his friends did back in the Point Venus to
Get wrecked, Captain Cook.
Yeah,
that guy's a loser, apparently.
But because we had a lot of help, including
right.
the very kind astronomers of 1882, leaving us some nice notes on recommendations. Other thing we also did is a visual phenomenon. So we, with this transit of Venus and transit of Mercury, we used instruments to calibrate the dip in light level of there. So Mercury was much less because it's a much smaller dot. Still had a dimming, and so we had instruments where we took the sun's light and we dimmed it right down with neutral density filters, and then had our planet detectors look to see could we detect the planet passing in front of it.
Right.
So it gives a nice little test subject.
Okay, well, that's pretty cool. So I think there was another big piece of space news, which was a unusually low mass black hole has been detected. Is that correct?
Yeah, I mean we there's a class of black holes that we don't really know much about, and that is relatively low mass black holes. And this particular black hole that was discovered has a mass we estimate around 3.3 times the mass of the sun.
Okay.
And so its event horizon, the point of no return, was only about 3.3 kilometers wide.
That's pretty darn small.
You know, two-ish miles wide. Now, black holes can in theory be very, very small. They can be 22 micrograms in mass, like what's called a Planck mass. But those things, decay sentiently due to their until this 3.3 solar mass black hole. The ones that smallest ones we knew were around 15 times the mass of the sun. And so, but we're getting better at detecting lower mass black holes. And of course, what you do is you don't really detect the black hole itself. You detect its effects on surroundings,
right?
And then infer that it's a black hole. So when you have stars that are like a neutron star, and they were somewhere around, we believe the neutron stars, when they get up to around 2.5 times the mass of the sun, the gravitational field becomes too strong and the thing collapses in on itself to form a black hole.
But wouldn't it have a type 1a supernova before it got to that point? Isn't the Chandrasekhar limit, or however you pronounce that word, lower than that?
That limit has to do with in terms of for example, if you have material on a white dwarf that gets to be 1.4 times solar mass.
Is it a white dwarf, not a neutron star?
For you're talking about like type 1a supernovae.
Yeah, I'm mixing things up. Never mind. Keep going. Sorry.
That's fine. The thing about that when you get a star, let's say that's 8 to 9 times the mass of the sun, and it undergoes a stellar collapse, a type 2 supernovae, there's a lot of material gets thrown off. You don't get a 9 solar mass black hole.
Right.
One of the things that happens is that the thing crushes. You get these enormous energy. You get these, this burst of neutrinos and other crazy stuff happening, and so the star itself throws off its outer layers. The model said that you need to have at least 2.5 times the mass of the sun that collapses inward, and the other maybe 7.5 solar masses gets thrown out. And so you get this sort of recoil where the inner part crushes it and forms a black hole. The outer part recoils and gets pushed out. So we expected then to find things as low as maybe 2.5 times the mass of the sun. So finding something that's 3.3 solar masses was a kind of nice. Yeah. So that's now it's around. It's situated about 10,000 light years away, so it's relatively nearby. But it's only 19 kilometers wide, so you're not going to be able to see the regions, even if you talk about the stable orbiting regions. Let's say, for example, if this black hole is not rotating, then a point 3 times that distance, or somewhere around 60 kilometers wide, would be the place where you'd have a stable orbit. Objects could increasingly just could move around unless they nudge each other and send themselves down the drain hole. Yes, and if you have the model says if you have a non-rotating black hole, where the event horizon is at 1, something orbiting at 3 can have a stable orbit and can orbit there till the cows come home, right? Or unless something nudges it inwards. If something is spinning fast, as it approaches the speed of light on the edge, the position of the stable orbit goes from 3 down to 1, right? And to a point where it would be traveling, it would have infinite mass and traveling approaching the speed of light, approaching infinite relative mass. The stable orbit would be right next to the event horizon. That's not going to happen, right? I suspect so. I'd be very surprised to find a non-rotating black hole. I mean, just the simple collapse of something and something falling in, it would have to basically everything would have to be sort of like perfectly gently coming straight down for it to maintain no set. So there are several things that we can detect outside of a black hole event horizon. So the black holes are not completely black. One of the things we can detect is charge. If this thing has an electric field, we'll detect the charge. Another is the effect of spin on orbits around it. And the third, of course, is obviously gravitational field. It's mass. So mass, spin, and charge are three properties that you can detect outside of the point of no return.
Okay. Okay. Yeah, and sorry, I had when I asked you that question, Landon, I was actually muted, but that was the no names question, which I actually was about to ask myself before he asked it, because it has always seemed odd to me that like the idea that we would encounter a non-spinning black hole, because why wouldn't it be spinning? Because it seems very unlikely that you would encounter an object in space that just doesn't have angular momentum. Like, why would it not?
And there are several types of black holes. There are stellar mass black holes, things that are, maybe 5 times the several tens of times the mass of the sun.
Right.
Because we think some of the most massive stars, before they blow themselves apart, may be approaching around 150 solar masses. So a simple star collapsing and the remnant forming a black hole is probably somewhere in the 2.5 up to maybe 100 times the mass of the sun. There are supermassive black holes, things that are between millions to billions solar masses that often show up in the center of galaxies and dominate how galaxies evolve and so forth. Then there are these intermediate black holes that are bigger than a star collapse, but not to the point where they're galactic core type things. But the galactic core has to start somewhere.
Right.
And so it might be the intermediate masses of basically a black hole that's growing. Then the fourth thing we talk about is primordial things, black holes that probably formed soon after the Big Bang as a result of the Big Bang process. And it's really the tiny ones, that could be there on the order of could be really quite small, but they decay fast, right?
Right. I was just supposed to say, wouldn't those have likely all decayed away? Any small mass primordial black holes?
Yes, I mean in terms of, but as I say, and so the ones that primordial, there's things that are formed shortly after the Big Bang. The ones that should be left, according to Hawking radiation, should be the ones that have a reasonable amount of heft. They're not they're not going to be small, but they're not going to be the micro stuff. I mean, black holes can certainly be as small as 1/10 of a millimeter. Those are the Planck-sized things.
Right.
They could be Earth moon size to quite large. And I think, by the way, that people to realize is that black holes produce sound. There are because of the way it sweeps around and the way that space is being distorted, there are sort of sound waves that they can generate, are called cavities around there. But they really do a lot of stuff. That probably the biggest problem is that approaching a black hole, you would be stretched, or we call spaghettified, before you crossed into the boundary. You basically die a really horrible death just approaching the point of no return.
Now, I seem to remember that this would be less of a problem the larger the black hole is, that tidal forces would diminish as the mass of the black hole increases.
Or the shear, right? Because the gradient, if you will, right? The thing that why something would be stretched is that the gravitational field at your feet would be much stronger than at your head, and so you'd be,
right. But
ripped apart.
That gradient would be lower if it were a higher mass black hole.
Yes. So the stellar and smaller masses have a really nasty gradient, and you'd be stretched much.
So if you have to fall into a black hole, fall into a supermassive black hole, I guess.
Yes.
But try not to fall into a black hole in general is my recommendation. I feel like most people would probably second that.
Sure.
Okay. All right. I have to step away for a second, but there's something I'm going to have to make fun of Bent a little bit, because recently Bent Hovind got a orbital mechanics problem wrong that Kent Hovind got right. And I want to see if you can explain this to Bent better than I could, because I don't think I did a great job. So I'll let Bent explain what the problem is while I step away for a second.
Thank goodness it wasn't on the air when it happened. But no, my understanding of escape velocity was that it was like a set value gravity planet. I was wrong. The higher up you are in orbit, the how that works.
So, if you think about what escape velocity says, is when you start in a launch position and you travel away from the center of mass, what speed do you have to travel at so that you won't fall back in? Right? Because like when you're on the Earth's surface and you jump up, you might jump up really high, but you don't jump up fast enough, and you usually stop and come back down. So as you move out of the gravity well, the velocity necessary to escape reduces. Right? Why? Because gravity is less. So you imagine and again, so the reason why farther away from the Earth, your escape velocity is less, is that you have less. There's a lower gravitational field, right? As you move away from the mass's inverse square, the gravitational field slows down. So you were asking specifically about, was there a specific scenario that you were looking at, or?
It was something that Kent Hovind was talking about in one of, and I was commenting Dapper Dino off the air.
So
being wrong when he was actually
right. So when you talk about escape velocity from the surface of the Earth, you need to be going at around 11.2 approximately kilometers a second. That's somewhere around 25,000 miles an hour from the Earth's surface. But now imagine that you move twice as far from the center of mass. So now your gravitational field is 1/4 the strength. Your escape velocity is 1/4 that. So instead of being at 25,000 miles an hour, you'll be at somewhere or around 6,000 miles an hour. Right? Now we're talking about impulse, right? You have a big cannon, you launch yourself. As you travel up, the gravity is going to slow you down. The question is it able to slow you down to the point where you would stop and come back, or you drift off? You drift off is escape velocity.
I actually have a question about escape velocity, and I think I know the answer, but I want to make sure that I'm getting this right. My understanding is that escape velocity is calculated as a two-body problem. So if, let's say, I reach escape velocity from Earth at some point, I have not escaped the sun. I'm now in orbit of the sun, and I could come back to Earth as a result of my orbit intersecting Earth, right?
But actually, let's say that the way that the formula, classic formula of escape velocity is square root of 2gm over r. So g is the gravitational constant. M is the mass of the body to be escaped from.
Okay.
And r is the distance to the center of mass of that object.
Okay. And are we assuming that the mass of the object trying to reach escape velocity is essentially negligible?
Yes, in that.
Okay. Okay, so yeah, it's not even a two-body problem. It's basically a one-body problem that we're working on here.
And so that'll give you so now that's for a spherically symmetric object, right? If you've got something with pointy bits and all that sort of stuff, that's a different story. So you would have to collapse the object into its spherical shape, equivalent shape.
Bob Knob says you need the mass of both, but I believe that for most calculation purposes, if you were to include, say, the mass of, say, a rocket that you wanted to hit escape velocity from Earth, and Earth itself, that mass of the rocket would get lost within the margin of error of your calculation compared to the mass of the Earth, wouldn't it?
Sure, and again, it's also the same thing as if it's so that relationship is independent of the mass of the object escaping velocity. So so if the object, for example, is at infinity, starts at zero velocity, it would strike the massive object with a velocity equal to the escape velocity. So if you start off at infinity and you're gravitationally pulled towards the object and you accelerate as you go the gravity towards the object, you'll hit the surface at escape velocity.
Right. That makes sense.
And that's independent of your mass, right? Now,
right.
where it can come into thing is that if you start, if your body is significantly more massive than it, you start changing the center of mass. Your barycenter becomes affected.
Yeah, your barycenter might actually be outside the surface of the object towards which you're falling, right?
And that's where but that technically that's not if your mass is negligible, so you don't change the center of mass to any measurable amount,
right?
Then you're fine.
Okay.
Now there is a thing for there are orbit trajectories where if you go to elliptical orbit, what's your escape velocity, the orbit trajectory stuff. There are certainly multi-body problems. There are things for relativistic stuff you can do. So for example, there's a if you have multiple bodies, you can talk about escape velocity in that sense for stuff. But I say the when we talk about the escape velocity of a body, we talk about what is the mass. Remember the formula. Let's go back to the formula again. The formula is square root of 2 times gravitational constant times your mass divided by r, the distance to the center of mass. If you're so massive that the center of mass is dominated by you, it's hard for you to escape. Right? The formula changes, right? Because you're going to be tugging the center of mass with you if you're. But it's distance to center of mass. So in fact, it's independent of your mass.
If you're small enough.
Well, no, period, right?
Oh, okay.
The problem is if you're the same mass of the object you're trying to escape, then your center of mass is not the center of that object. It becomes a center of mass point between you. As you move, your center of mass is going to be moving appreciably, and so it becomes more messy.
Yeah. So
there's ways to handle that if you have significant.
But I guess if I were trying to build a rocket that was going to hit escape velocity, the chances of me building a rocket so massive that I have to take into account the mass of the rocket in terms of what velocity I need to hit is going to be extremely unlikely.
Yeah, because the force, the force formula is that g, gravitational constant, times the product of the two masses divided by the distance between their centers squared.
Right.
G m1, m2, or r squared.
And if one of them is one Earth mass and the other one is, a few thousand kilograms, well, a few thousand kilograms is basically nothing.
But the work, the work needed to move the body over a small distance, you define by a gradient, and that gives you an integral that you can go from radius up to infinity.
Thanks, calculus.
And that ends up basically when you do the work necessary for the kinetic versus potential energy, you come back to square root of 2gm over r.
Okay. I'm trying to think. Have there been any other recent astronomy discoveries that you're aware of?
Well, there's a number of things that are happening all the time. Those were a couple of things. I think, for example, one of the areas that we keep looking at, that we want to go back and explore, is the sort of with the ice giants on the outer edge of our solar system, namely Uranus and Neptune. And revisiting those are going to be our proposed missions that are going to be really quite important.
If I remember correctly, the only thing that humans have had that was close to Neptune wasn't it one of the Voyager probes?
Yeah.
And it just kind of flew by?
Yep. We learned a lot, but we'd like to know a lot more because it raised lots of questions.
Right.
So we have certainly there's we have an interesting case of a planet around a nearby star that appears to be on a steady spiral inwards, right? Its orbit is decaying, and so we may end up seeing or observing the effects of the star swallowing its planet.
Now, what would make the orbit of a planet decay? Because that's not something that seems to happen in the solar system, at least not in any appreciable amount.
Well, it could be. I mean, part of it could be by tidal interactions, interactions with another star, interactions with other planets orbiting the same star, can cause things. So, so those are. But we're looking at it to see that the other possibility is that the object is slightly elliptical, and that ellipse is evolving over time. The eccentricity is evolving over time because it might be interacting with another planet.
Okay.
We don't know about that's causing it there. So that's a little bit of a thing. We had a nice thing of a supernova that destroyed its stars. We had nice case of it was a case of a that we have the parent star, and it went supernovae, and the initial star had an initial mass around at least 100 times the solar mass, and we basically watched this thing go poof, and the result was that it destroyed itself. They're only 54,000 light years away, so it's not dangerous to us.
Right.
It was a really nice thing to see.
Beach Price says, Landon, do you think there are any stupid questions? Because Beach Price has a question.
No, I don't think so. I think because science is all about questions. And science values. I mean, science. It really is. It's questions, and if you get results from your questions, then that leads you to more questions. I mean, that's dogma gives you answers, but science gives you questions. So the question becomes, I think you could do something ignorant with a question by saying, not doing something useful with it, like saying, well, because, right, as opposed to, but I don't think they're really a stupid questions.
Okay. Well, hey, ask that question, because
I mean, there could be questions that could be better formed, but a question can be initially proposed, and we can figure out how to improve the question if, in fact, we have a better idea of how to say what we want to say.
Right.
We may have discovered a moon around a planet around a nearby star.
Really? How was that? Assuming that it's true that we did that, how was that accomplished?
It was done by there were two. We believe that there's a planet with two moons, large moons that are relatively significant size, that's causing the planet to sort of wobble in its orbit around around the star. And now we're trying to get independent confirmation, but we may have discovered our first moons around.
And Abijah, it wasn't a star that has the moon, exoplanet, right? That has
two
moons apparently.
Yes, we think that's the model to suggest it has two moons.
Okay.
That are significant size compared with the planet itself.
So Bijah asks, if the sun stopped rotating, what would happen to the planets?
If the sun stopped rotating, the planets would continue in their orbit because the sun's mass would be the same spot, right? We orbit because of the mass of the sun, not necessarily because of spin. Now, okay, if the sun is spinning rapidly, its its equator is a bit more bulged than it's a polar because its centrifugal forces to throw it out a little bit. But and there'll be tiny effects with the shape of the sun being more less circular, right, than would it be if it was sun was staying fast. Same thing if it was still, we still have the same amount of mass on at the sun, so we still orbit it.
So more or less, it wouldn't make much difference as far as the planets are concerned.
Yeah.
Okay. So I guess this is not technically astronomy, but it is space news, which is the SpaceX launched some 60 satellites for their Starlink project this week, which is their project to get satellite-based internet to essentially the whole globe, as far as I understand it. That's pretty cool. It's not quite astronomy, but it is space-related.
And I hope the transmitters are well tuned. They're not broadcasting all kinds of nasty frequencies like the old Iridium satellites were. Some people worried about the space debris and junk that's there, but I think if they do it well, it would be a welcome addition to the other technologies. The new Iridium satellites that don't have all those nasty Iridium flares, and are much more. They have much more powerful transmitters, more well tuned, are also giving us global communication. But I think having multiple ways to have universal ground-based communication is a good thing.
All right, and we have a question from Puffalopagus. How likely is it that we will discover a moon with its own moon?
Great question, and I like Puffalopagus's. Hello there, Puffalopagus. There's no reason why a moon couldn't have a moon. The reason why we don't see moons around some of our moons around our planets is that usually the planet has ability to disrupt the moon's moon, or other moons nearer the moon disrupt the moon's moon, right? So in theory, it could happen. It's never been observed in practice, and we're looking.
And I would think also that a moon's moon would have to be even smaller than the moon in order to maintain that orbit. Like, would have to be significantly smaller. So it would be significantly harder just to find in the first place, wouldn't it?
Yeah, because I would not call a double moon a moon's moon, right? Because that if you have two objects that were the same mass as each other that are co-rotating,
right?
Like you have a double dwarf planet like Pluto and Charon, is two planets orbiting each other.
Pluto's bigger, but the barycenter is outside the surface of Pluto, right?
Yeah. So yes, and so you have moons that shepherding moons that sort of dance around each other. So I wouldn't call the one the moon of the other. What I would say if an object is a moon of a moon, its common point of orbit or barycenter needs to be inside the more massive object.
And I would say I would really want it to be fairly close to the center of mass of the larger moon. I mean, if it's like halfway between the center of mass of the larger moon and the surface, that's you're getting into that weird territory there.
So if you would have a really good moon of a moon, you'd want the mass ratio of the big moon, small moon to be pretty good, so the common orbits around the middle. Right. But again, of course, as that pair gets closer to the parent planetary body, it'll be harder for that moon's moon to maintain its orbit and not escape and become a direct moon of the parent body.
So I guess the ideal situation would be you'd have a moon orbiting pretty far out from its host planet, and it itself would have a moon that would be significantly smaller in mass than that moon, and there wouldn't be a lot of other moons to cause weird interaction.
Yeah. So there's nothing wrong with that. There's nothing wrong with that. And we've looked for it. We just haven't found any.
Right. Yeah. It's just one of those, the circumstances aren't super likely in any given instance, but there's no reason it shouldn't happen ever, right?
Yeah. And so we've not seen that in our solar system amongst the planets and dwarf planets that we have. And we've seen asteroids with moons. But we've never seen an asteroid, but again, that's like a sub dwarf planet having a moon. We haven't seen a moon of a moon. We haven't seen a asteroid of a moon having a moon, right?
Could our moon have a moon?
Well, in theory, you could try, but again, it would be unstable, and Earth would end up snatching it.
Well, and I also know that the moon has enough gravitational like asymmetry that even man-made objects in orbit tend to decay into a. They tend to lithobreak, if you will.
Yes.
Which is one of my favorite terms, lithobreaking.
Yeah. And so if our model of how the Earth-Moon system formed in the first place is reasonably correct, the moon itself would start off as a ring debris from the initial impactor of the Earth that destroyed the proto-Earth some 50 to 100 million years after its formation, and so the Earth for a period of time had a ring that accreted to the point of forming the moon. But most likely that ring still had an initial lump. The bullet that hit us, or
maybe the core
of the object, probably was the biggest lump in the ring. So it probably wasn't like a nice ring like Saturn stuff. It was probably a lumpy ring.
Okay. Let's see. Did they ever decide how many moons Earth has? I saw them talking about that for years. I know that every once in a while Earth gets a sort of temporary thing that goes around a few times before it's either ejected or impacts something. Yeah. But as far as I know, there's only one permanent natural satellite known for Earth. Is that true?
That's correct. There's only one that has a permanent thing. There are quasi-orbits for something that has a dance where it comes in, it gets near Earth, it dances around for a while, and it gets ejected again. So there's quasi-periodic objects like that. But again, you wouldn't call something that escapes and wanders around before coming back to its parent body that wouldn't be a really good moon, as you say.
Yeah, sort of a temporary moon, maybe.
Yes.
Okay.
Yes.
And it's my understanding that Earth, it's not unusual for Earth to have one of these. Like, it has one a fair portion of the time. Some tiny little rock that's going to orbit a few times and then get kicked out eventually, right?
Yes. And so there certainly are people that have claimed existence of stuff. So, for example, there was an asteroid that was possibly the most stable quasi orbit of things, and it's called it says 20. It's 4. I'm looking at the paper. I'm thinking of the paper in my mind. 469219, and it's Como something or other. There's an asteroid that was discovered in 2016 that has this kind of dance where it's roughly in Earth's orbit, and when the Earth kind of catches up with it, it spins around Earth for a while and it gets ejected and does another orbit around the sun. So it kind of switches between orbiting the sun and orbiting the Earth.
Okay. So maybe it's like a half moon.
Yeah, it's called quasi-periodic stuff. It has a fairly weird path.
Ben, do you have any questions? Because
I had a question the last time you had Landon. Typed in the chat, but got a lot of good.
Well, what was it?
You were talking about I think black holes a lot. I was wondering about a white hole, the mathematical opposite of a black hole, and if Bang described as white hole.
That's a fancy mug you got there.
So, just had to show.
Yeah, why don't you show the mug up for the audience to see?
Let's put that up there. Yeah, so on the website, it only shows you the color side, but there's also a grayscale side on the other side, so you get twice the dapper for the price of one dapper somehow. I don't know how that works. But you want to hold it up one more time just to let the people see the two sides again? With the color side? Yeah. In real life, there aren't any low resolution problems because of bandwidth or webcams or anything, so don't worry. So yeah. So Landon, what's the deal with white holes? They seem to exist in the math, but are they real?
So basically they're white holes in some ways are like black holes. They have properties like mass, charge, and angular momentum if they exist. But they attract matter because they have mass, like other things. But in the case of the white hole, the objects falling towards it would never actually reach the event horizon because of this sort of this the what's called extended Schwarzschild solution. So so what we'd have is a compact object which you could never reach it. You'd have to go too fast, or that relativity would disallow you before you could get to the spot. It's one of the ways. We don't know of any white holes. It's a mathematical construct, but remember, the universe doesn't really care what our models are. The universe does whatever it does. To say you've got a mathematical model that says that white holes should exist presumes that your model is actually an accurate description of reality. There's a number of things we don't know about black holes to suggest that we're learning. And so to assume the math would allow for existence of a white hole means that white holes exist it's really a tenuous distance. I mean, it's possible, and there are papers that suggested that the Big Bang was a white hole, but they propose some that matter was ejected by a single pulse, and that so what they're doing is they're saying, well, could we classify the Big Bang event as being a white hole event?
Right.
And so we'll say, well, that sounds like you're kind of it certainly has been there's a paper in 2012 that asked that question, but the authors, I think, of that paper are not saying it is. They're asking the question: could the mathematical definition of a white hole, the object that has mass, charge, and momentum, but and attracts mass, but you can never actually reach the event horizon, could that be a description of the Big Bang process? And so they're not saying that Big Bang is a white hole, but could you take that process mathematically, describe the Big Bang as if it were a white hole?
Could we? Does it seem like we could?
It explored that. It didn't actually come to a conclusion. There's the idea of a Big Bang produced by a supermassive white hole explosion was also explored in a paper in 2014 as well. And so these are not people saying it is. They're saying, could you build a mathematical framework that would sort of satisfy what we observe and what the model suggests that they should be like?
Okay. We have another question.
They're asking a useful question.
We have another question from Puffalopagus. Can Landon explain what they think is causing what we believe are antimatter fountains in our universe? And I don't even know what he's going on there about. I haven't heard anything about that.
I haven't really heard of antimatter fountains. We know that antimatter gets created in our universe from time to time, but it tends to be short-lived because it finds matter and annihilates it. So, and so whenever you have that famous equation by Einstein, E equals mc squared, when you take energy and convert it into matter, you end up producing what appears to be equal amounts of matter and antimatter. So energetic photons can actually form, let's say, an electron and a positron, that is an antimatter electron pair. Right. And usually what happens is the positron finds another bit of matter and annihilates it, is often what happens
All right, we have.
But we don't know of any region of space that's dominated by antimatter. In fact, that's a big question. Where is all the antimatter? We'd expect to be a lot of it around, and
So I was
doesn't have
linked a paper, or not a paper, but an article from Astronomy.com saying there's a Milky Way antimatter fountain. Apparently, it's a bit long to go over just on the stream, but so do we have any good? And I'll try to read that later because that does sound interesting. But do we have any good reasons as to why the universe should be dominated by matter as opposed to antimatter?
Okay. Well, there's one thing that this may be a misnomer. By antimatter fountain, in the center of our Milky Way, we have a supermassive black hole.
Right.
Although not as massive as ours, only like 21 million solar masses. And
Oh, is that all?
Yeah, and we've got ones that are in the number of billions. So we're kind of a lightweight as far as our galaxy, as far as black holes. And around that event of material that's sort of in those stable orbits, but in highly energetic states, you'll get production of very high energy X-rays and gamma rays, and those actually gamma rays can end up decaying into matter and creating electron-positron pairs, for example. So the fountain they're talking about is that they're saying that there's antimatter radiation, antimatter being created near the black hole, but that antimatter radiation finds other matter quickly and annihilates it. So you get an area that they think might have, and it's a region. It's a region near the massive black hole where antimatter could be formed for a short period of time before it decays into a burst of energy.
So, but do we have any good ideas as to why? All right, so it seems like most processes that can create matter or antimatter essentially create both of them in about equal amounts.
Yeah, and in fact, every time we've done that, it's always been equal amounts.
But the universe seems to have a strong preference for matter in terms of baryonic particles floating about in the universe. So why is that? Because it doesn't seem to me that there should be a strong preference. Or is it actually a strong preference? Are there antimatter galaxies out there? How would we tell?
I mean, this is a really big problem called the matter-antimatter asymmetry problem, and we don't know why matter dominated itself. And it appeared from models that matter outmassed antimatter by a factor of 1 part in a million, enough that the early universe didn't turn into just a bunch of photons, right?
Right.
And so whatever process, so one explanation is whatever process occurred in extreme conditions around the Big Bang favored matter over antimatter, just slightly, so that the two annihilated each other, and we've got this imbalance left over.
Right, there's a remnant of matter.
Yes, and so we've been looking for precise measurements about matter-antimatter, balance, to see is there something that could end up explaining what was going on. But this is one of the things that they're actually exploring at CERN, the big atom smasher in Europe. Okay. Is this business about and it's one of the great challenges on there is to find out, well, why is there somewhere in the particularly in extreme conditions a favoring of matter-antimatter that they're not truly symmetries of each other. So one of the reasons why they've been creating things like antihydrogen is experimenting with antimatter and doing measurements to see is it slightly different, right?
Right. We have a question.
But we don't know. That's unfortunate.
Now, actually, I do have a quick question. Let's say that a galaxy were in fact made of antimatter. Could we tell from Earth that that was the case?
Most likely because that galaxy would be interacting with other intergalactic visitors. I mean, just like we have objects that pass through our solar system, they're interstellar.
Mm-hmm.
There are objects that are intergalactic. Those would be even rarer. But if for example that comet were antimatter passing through the sun, all the particles from the solar radiation that were hitting it would be causing annihilation. You see these gamma ray flashes as matter and antimatter is annihilating each other. Same thing, inside a galaxy, it's not a pure vacuum of space. There's actually material between the stars.
Right, the interstellar medium.
Yeah, and that has stuff, right? And so if you had antimatter interacting with matter, be it one or the other, you'd see these annihilations occurring, and you would see the characteristic matter-antimatter collision. So, for example, electrons and positrons would be creating gamma ray photons at what? The mass of the electron, 511 kiloelectron volt gamma rays would be coming from the spot where the electrons and positrons were annihilating each other.
Okay.
So you'd have to have something which was somehow isolated very, very well, and the interactions with matter and antimatter were so infrequent because it's some weird bubble that we couldn't detect it with our best telescopes.
So what I'm getting is that episode of classic Star Trek where there was the guy from the antimatter universe and he was crossing over into our universe, not a very realistic episode.
Not realistic.
Okay.
It's good. It's a good story.
I mean, it was a good story, and the ending was pretty good. And if you haven't seen that one, I don't even remember what it's called, but it was quite good. Yeah, but let's see. We have a question from Chuck.
But actually, for the Big Bang, it's actually 1 part in a billion.
Oh.
If there had been 1 part in a billion, it appears to be that 1 part in a billion more matter than antimatter after the Big Bang, resulting in us.
So it seems like there must be something that's different besides what we normally think of as the differences between matter and antimatter.
And we're looking for that difference. We're measuring. So far, matter and antimatter appear to be pretty much the same, but it could be a subtle effect that we don't understand.
Okay. So let's see. We got a question from Chucky McNubbin. Could those supermassive galactic powerhouse black holes be the reason why galaxy clusters take such a large amount of time to spread apart?
We think so. Although the other thing, certainly, it appears that there's a relationship between the mass of the central black hole in a galaxy and the mass of the galaxy. But the other thing is that's probably even more dominant is dark matter.
Okay.
Stuff which is much more massive than the star. And on average, your average galaxy mass of 1 has a dark matter mass of close to 5.
Yeah.
Or 6, right? So dark matter actually dominates in the gravitational field that dark matter produces, whatever it is. That gravitational field dominates the galaxy much more than the central massive black hole. So again, look at our Milky Way. And again, if the numbers, the number strikes me as around 21 million solar masses in the center of our Milky Way. Pardon if that's wrong, but it's something on the order. It's a handful of millions. We have somewhere close to a quarter trillion stars, around 200 billion stars in our galaxy. So we have at least 200 billion solar masses in our galaxy, of which the black hole is less than 1/10,000th.
Right.
Now, take the dark matter that's associated with it, where you have 5 times more dark matter than the entire mass of the rest of the mass of the galaxy, and the dark matter dominates the mass of the central black hole by several orders of magnitude.
Okay.
That being said, don't underestimate the influence of that central massive black hole on how the galaxy evolved. Both are quite important.
But on the scale of a galaxy cluster, the black holes themselves are probably not the dominant effect.
They're certainly, they seem to be a formed as a result of. So we think the reason why the bar galaxies of a certain type have a mass that's proportionate with the little black hole has to do with how the galaxies are formed. They might be because of the black hole itself, but that may be a byproduct of how the galaxy gets formed.
Okay.
We know those are great questions.
Yeah, no. Look, my audience asks some pretty darn good questions, I got to say.
Excellent. Those are excellent questions.
Yeah, I have very intelligent viewers who come up with very interesting questions. I am very happy about that. That's been something that has been the case, not just with your streams, Landon, but just in general. My audience is extremely good at good questions. And by good questions, I mean questions where it's really hard to know what the answer is, and in many cases we don't. I think the best questions are the ones where we're just like, I don't know, that's hard to say.
But as I say, one of the things you can do, however, is then the question of ask those questions and explore it, because that's certainly part of the scientific process.
Oh, yeah.
And by the way, if you like this sort of intelligent discussion, I would highly recommend that you help support the intelligent discussion. And that includes, I assume you have a Patreon?
I do actually have a Patreon. Yep, I have a Patreon. I have a merch store, and I have an Amazon wish list. Actually, the microphone I'm using now was purchased by one of my patrons from my Amazon wish list. So one of my patrons out there, who I believe is mentioned in my next video coming out on Tuesday, has been double dipping into the support. He's been triple dipping because he bought merch and this microphone that I'm using right now, as well as being a patron. So
well, thank you very much for that person doing that. And so if you like this kind of content, my recommendation is support it, please.
Yeah, and the flip side of that, of course, is if you can't afford it, please don't. If you can't afford to do any of those things, what I would ask that you do is like the video, make comments on my videos, and share it.
That little like button.
Yeah,
right?
hit the like button.
Share it.
Right.
That's another way to support it. I mean, there's certainly financial support helps, but
it
also
does.
Word of mouth support is also extremely important.
Yeah, so. I'm hoping in the long term that I can get this to be the thing that I do pretty much full time. I don't think that I'm going to be able to do that right now. I'm probably going to have to go and get another job at some point pretty soon, because currently my expenses significantly exceed my income from this channel, which is fairly small. But the more I get from this channel, the more I can put into it, and the more I can cut back on other things, because I'll be honest, being someone who can help spread, science knowledge as a science kind of communicator, sort of a dream job for me.
Sure.
And I think I'm decently good at it, so, let's see. Let's see.
For a dinosaur, you're pretty good at it.
Well, thank you. Beach Price recommends that I do an interview at Neil's, and actually, yeah, that is scheduled. I can actually double check when that is scheduled. I haven't posted about it yet because it's still a fair bit of the way off. So December 9th, I'm going to be on Neil's show. I believe it's called Deconversion Stories. I'm going to be talking about me leaving Young Earth creationism. I don't, on this channel, discuss my personal religious views as such, so I'm not really going to get too far into that, but I will discuss my leaving Young Earth creationism, the things that led up to it, which is a story that I've told on this channel, but, I feel like a lot of Neil's viewers are not going to be people who are also watching me at the moment. So there's that. Let's see. Puffalophagus asks about Hoag's object and the separate but similar galaxy seen inside its outer ring. I don't know if you know much about that. I don't think I've ever heard Hoag's object. It's Hoag, and I think it's supposed to be apostrophe S, but he has it just as S. Or if we want to be all military about it, we Hotel Oscar Alpha Golf.
Okay, okay. Hobes. I was hearing Hobes and something.
Oh yeah.
So that's it's a ring galaxy. That's actually quite nice. A fairly peculiar galaxy that was discovered in the 1950s. And it's in the constellation of Cepheus, Cupid. So it is it's peculiar that it has sort of a bright sort of yellowish whitish center, and it's got a ring of blue stars around it that in a fairly symmetrical way that is quite peculiar. Yeah, the model is that this is formed by a collision or merger between a fairly small galaxy, dwarf galaxy, and a larger sort of disk style galaxy, and it created the collision created a sort of density wave that caused concentration of star formations at sort of a preferred distance from the center of the combined set, and so the ring of stars is a result of the shock waves that created a starburst, but in all directions. It was so you had a disk, you had a galaxy that was in a plane, and another dwarf galaxy collided with it. The resulting collision and shock wave went out and hit the disk at a preferred spot at roughly the same distance, and those stars formed around that ring with the shock where the shock wave hit it. It's a fun, beautiful object. Yes. Yeah, well, there's probably a bunch of those that are edge on that we don't know are interesting. Now this particular object is around 16th magnitude in visual apparent brightness, so it means that you would need a pretty large telescope in order to see this object. I mean, we're talking about something that is maybe 30, 40 times fainter than Pluto. And to get any kind of detail, you're probably going to be needing a fairly large telescope in order to see it in detail. It was discovered in, I think, around 1950 by a guy named Hogue. That's why it's called Hogue's object. And it was that late because you needed to have at that time was long photographic exposure to show this ring. And it had the initial appearance of being like one of these so-called planetary nebulas or ring nebulas, but it turned out to be a galaxy that had this peculiar side. So the Hubble gave us a really particularly beautiful example of that set. And of course, as you say, the Hubble showed that there's a more distant galaxy that also has a ring around it. Yes. Okay.
Sorry about that. I'm muted again. Because I'm some kind of an idiot or something. I don't know. So this is a question from Oshkosh Bagosh. What's synchrotron radiation and its relation to AGN?
So AGN is an active galactic nuclei.
I think so.
Nebula. So I think and synchrotron radiation occurs when you have a charged object being accelerated in big accelerated particularly in a. So we find, for example, synchrotrons, atom smashers that spin stuff around, generate objects that are in that curved arc are accelerating. That's you're changing velocity, and that acceleration causes radiation to occur. In fact, that's quite useful. That synchrotron radiation is quite useful. There are medical uses of it. There's also, it's as a radiation source for doing detailed analysis, including determining forgeries of art pieces. They've used synchrotron radiation to penetrate underneath the surface and try to determine, that the surface was essentially created by a clever forger, and that the underneath substrate was the wrong material, as an example. So synchrotron radiation occurs when you have now active galactic. Is it nebula?
I think it's nuclei, but I'm not positive.
Nuclei.
I think it's nuclei. So is there a connection between the radiation that they give off and the synchrotron radiation?
I don't believe so. I mean, the AGN, active galactic nucleus, I think is the it's called. I'm sorry, it's active galactic nucleus. That's what that's AGN refers to, and so an example is a black hole region. The region around it has is called a is called an active galactic nucleus. So the accretion disk of the material spiraling in. This is well outside the event horizon of a black hole. That region generates jets that are typically perpendicular to the spin, and so these AGNs, active galactic nuclei, are compact regions that are in the center of the galaxy. Now the question is, okay, we have charges that are moving around, flying around the black hole, just like they're spying around in a cyclotron. Could they be generating synchrotron radiation? Well, the answer is yes, but there's a much more. But that radiation would be relatively, I think, relatively small compared with the more obvious radiation of you have materials being crushed and heated to millions and sometimes billions of degrees Kelvin, and that simple sheer high temperature collisions of particles is radiating all kinds of energy. Why do the jets go perpendicular to the whirlpool? If you were to pull up on the Wikipedia page active galactic nucleus, you will see they have a really nice picture of what's called an inner structure of a galaxy with an active galactic nucleus. And you'd see inside that, that they point to an accretion disk. So if you go active galactic nucleus Wikipedia, and the first sort of thing, and it says inner structure of a galaxy, you throw that up.
Yep. Here we go. Inner structure of an active galaxy. Ooh,
right. And you see the jets are coming out perpendicular. One of the reasons why the jets prefer to go out perpendicular is that the radiation that radiates in all directions. So you do have radiation that's going in all directions, but the radiation that's going in the plane of the AGN is going to encounter other material and be absorbed and re-radiated. It's the jets that are perpendicular that has sort of the free travel. That's why it goes both directions, right? Basically, you have this entering of the disk. As you get closer to the black hole, the conditions become more and more extreme, and you have higher and higher radiation. Yes, some of that can be charged particles that are particularly interacting with the magnetic field of the black hole. Because remember, charge is one of the things that can escape out of the black hole. You can get some synchrotron radiation from that. oftentimes the synchrotron radiation is actually would have a preferred direction in the direction of the actual accretion disk, not perpendicular.
So we're probably not seeing very much of
but,
that.
But there are forms that will go in all directions, right?
Okay.
But I would suspect that most of the models of the accretion disk comes from basically what's called inverse Compton scattering photons, and it has to do with material that and that material that is has called this inverse Compton scattering process is one of the processes. Now that is a process that's sort of similar to the synchrotron radiation stuff, but it's not quite like that. So okay. I guess the answer is I could say yes. I would expect there be some synchrotron radiation produced near the as you get close to the event horizon. But I think I don't think it would dominate. I'm just thinking about this, but it really is sort of a Compton effect set, which you could sit there and say, well, what is synchrotron radiation itself? Well, again, it's the result from acceleration of particles.
All right. Well, I think that's probably going to do it for us for tonight on this stream. Oshkosh Bagosh has a lot of questions regarding active galactic nuclei, but Landon and I have basically said that we would like to do hangouts about once a month. They're not super regular, but you can expect another hangout sometime in December, unless I'm incorrect, Landon. Is that what you would like? Yeah.
Yeah, I mean, because I have expedition in Australia, and another thing in Hawaii for doing some monitoring. So it may be hard for me until the beginning of the new year. By the way,
then it might not be till January or so. But there will be another Landon hangout on this channel, and so if you have questions for Landon, write them down someplace and stick them to your computer or something, because this is not the final time that Landon is going to be on here. But thank you so much for coming and watching. I've had a lot of fun. You guys have had great questions.
And very, very good question. And could I just give a compact statement? I've been thinking more about that.
Oh yeah, go ahead.
Radiation problem is that typically so the magneto is bounce along radiation or synchrotron radiation tends to be in the plane of the arc of acceleration. So I would think that the synchrotron radiation would have a preferred radiative power along the accretion disk, which would be absorbed by other material in there. Now that could heat up stuff, but I think that more likely the active galactic nucleus center is going to be caused by more of the inverse Compton effects.
Okay.
So I would advise you to look up synchrotron radiation, look up inverse Compton effects, and you'll see that they're slightly different properties. Although I wouldn't rule out synchrotron radiation as one of the things, but probably a minor effect.
Okay, well there you go. I think we can end with some plugging stuff. Other than my Patreon, my Amazon wishlist, and my merch store, I don't think I have anything to plug. If you guys like this content and you can afford it, and I want to emphasize that strongly, only if you can afford it, please give a look at some of those things. I think I have some pretty decent patron benefits. For $1 a month, you get access to early videos, you get access to a few exclusive videos, patron-only polls, and the Discord server for patrons only. And it only goes up from there. So I think I have some pretty decent Discord rewards. In fact, if you're a patron, there's right now a video that you can watch that's coming out Tuesday. You can just watch it right now if you want to. It's like a 22-minute long video, and you can just go ahead and watch it for $1 a month.
But even if you just want to share
Yeah.
the thing or tweet about from useful stuff from a Dapper Dinosaur, that's fine too.
And like really, if you can't or even just don't want to give any money, but you want to support the channel, like the video, comment on it, and share it around. Bent, do you want to plug your band website?
Coppermagma.com. Dapper Dino.
And the Seabad Show, right?
It's all free, so you don't have to pay any money to support the band.
Yeah, if you want some free metal, check out.
You sell merch, but I'm not going to ask anyone to buy any.
I'm going to ask people if you like. So go check out coppermagma.com, download some of the songs. If you like them, Copper Magma has a Teespring store where you can buy Copper Magma mugs, T-shirts, and a bunch of other stuff, right?
Yes, a lot.
Okay, so yeah. So coppermagma.com, check that out. And last but not least this time, Landon, what would you like to plug?
Well, a couple of things are there. If you want to have a good laugh, check out my good friend Pimp Monk. If you want to think about things that are in the crazy realm of religion, check out the Milwaukee Atheists. Folks there, they're a fun thing. Other sciencey bits, of course. There are a number of fine science channels out there that I would highly recommend. Of course, I would be remiss if I started naming some. People say, "How come you didn't name mine?" But certainly, this is a channel that you should look at. But Steve McRae's got some interesting content there. The Gig Room people do interesting technical stuff there.
Steve McRae, who told me he wouldn't be streaming at the same time as me, but then ended up doing it anyway.
Yes, and so you could tell him that I would have rum and coked with him, but instead I had to focus on the more serious things, which I think, by the way, your audience had excellent questions.
Yeah, my audience. I say this, and I know it sounds tacky and fake, but I really do have one of the best audiences. I love all you guys. You guys have great questions and everything.
And again, science about questions, so yay,
absolutely.
Yay audience.
So what I'm going to do is I'm going to mute us, and we're going to leave you with my intro video again. So thank you again all, and good night. So you found the skeleton. How would you tell people that? You personally, how would you decide?
Well, interesting question. I don't know. I'd have to do some research on that.